I'm going to do a second example now. I'm not going to go as far into the math because for this situation in particular, it's really important to get the visualizations right because this might be trickier than you realize if you just jump into it and start some calculations. So in this situation, we have a 500-gram model rocket with a weight of 4.90 newtons, and it is launched straight up. The small rocket motor burns for 5 seconds and has a steady thrust of 20 newtons. What maximum altitude does the rocket reach? So now note that this 500 grams is the same as 0.5 kilograms, but this does appear to be a 3 sig fig problem. So expressing it as 500 grams actually means, hey, this is 3 sig figs. Now you're told a weight. And one thing that I'm going to point out is in the next section, it clarifies between weight and mass and gravity, but effectively we can say that this is the force of gravity. We'll make some clarifications in the next section. It is launched straight up, okay, but now note that we have a time and we have a question about altitude, which sounds like delta y. But we have one more force here, which is going to be a thrust force. Okay, so we know the magnitude of two forces. We know something that is happening with a model rocket. So the object that we're interested in is the rocket. But we again see that we're going to need to bring in kinematics since there's a time and a position involved. So part of why I wanted to talk about this problem was it is going to be very easy to make a mistake in this if you don't actually model the motion. So I won't do out the math, but let's first be very careful about drawing the motion representing what's happening. So first is going to be the kinematics component. And something to think about is that it starts at the ground. We have an initial position in y, right? Note you've defined your coordinate system. An initial velocity, which we're going to say is 0. It's starting from rest and accelerating upwards due to the rocket. And a time 0, which is just 0. So it's accelerating upwards due to the rocket, a0y, right? So this is when you have thrust. But at t1, the rocket stops burning, right? That was 5 seconds. So the rocket engine is now off. Does it immediately fall? No. And something important to realize here is you have this V1, and we don't know what that value is, but V1y is definitely greater than 0. It is still going upwards at 5 seconds. It has been accelerating upwards the entire time. So certainly V1y at that moment in time is up. So there's a second period of motion. And note that in the second period of motion, we now have a downwards acceleration, which is just gravity. This should make sense. After this point, it's in free fall. So when we think about models, here we have a constant force situation. It is not going to be a equilibrium situation because there is an acceleration. Up here, we also have a constant force situation. But be careful because this is different than this one. We have two periods of motion where something different is happening. So if I actually made, for instance, an acceleration versus time plot, it would need to also go negative, and we would have a positive acceleration until 5 seconds, and then we would have a negative one. So this is t equals 5 seconds, and then down here we have negative 9.8 meters per second squared. So you have two periods of motion to worry about. That's important because it means you need to actually draw two free body diagrams. Different things are happening here. So I'm going to clear off this ink so you can see a little better what's happening. Okay, so this sketch was really important, and this picture then turned it into a motion diagram. And I would really encourage that here, since again, this points out that your acceleration is going from upwards to downwards. You had a maximum speed here, but the maximum speed is not when you have your highest altitude, which is what you're trying to find. So we have our motion diagram, we have our sketch. We now think about our forces. The only two forces we worry about here are our thrust force and our gravitational force. That's in this lower case when we actually have thrust. In the upper case, we only have gravity. At that point, the engine's not burning. Why don't we have a normal force? Well, it's in the air. It's not on a surface. And this is a case where we're ignoring air resistance because air resistance would not actually be a constant force. So we then think about two different situations. We have our free body diagram here, where we have gravitational force and thrust force. Note that the net force is going to be smaller than the thrust force because gravity still pulls down. But now that you have your net force, you can calculate the acceleration here. Now here, you actually don't in a way need to calculate that because you just know that this is negative 9.8 meters per second squared. But here in particular, you would need to calculate that acceleration, and then you go back to this being a kinematics problem. So the kinematics question here would actually be a little more complicated since you have to use the initial velocity you get from this, the velocity here, y1, that was your final velocity from the first period of motion, becomes the initial velocity for your second period of motion, and then you find this total height. So not going to do that out since that math would primarily just be a kinematics question, but be careful because again, in force situations, force problems, you might need to break up periods of motion just like you did in kinematics. So that's again why you want to draw a good sketch, label your variables, and seriously consider drawing a motion diagram, especially if you have different periods of motion occurring. Now to briefly summarize, once again we are stating that net force is equal to mass times acceleration. F equals ma. Keep saying it. Now this is holding true if we're thinking about it as components, the x component and the y component, or if we think about it as a single vector. And by that, it means that whatever direction your acceleration is in, your net force must be in that direction too. Now again, it's important to draw your free body diagram, draw your free body diagram, draw your free body diagram. After you've done that, then you're going to be using Newton's second law, where you're relating your acceleration to your net force. Now, in the previous section of videos, we talked about this being 0 due to the equilibrium model, but now we're using the constant force model, so it's not 0, but it's some constant value. Finally, it's really important that when you're tackling these, you're identifying what is about force and what is about kinematics, i.e. motion. And so acceleration is what's going to tie together what's happening in terms of forces and what's happening in terms of time, velocity, and position. So you want to draw more than one representation because forces need free body diagrams and kinematics need plots, sketches, motion diagrams, whatever makes the most sense for that situation and for you. So please be very careful when tackling this. We will continue to develop this over the next few sections, but it's going to get more complicated as we worry about the details of different types of forces.